the new chapter, hydrocarbons. Hydrocarbons. Okay. Hydrocarbons. Ready. I think organic basic principles over. Basic principles is over. Right. Okay. Ready. Hydrocarbons. Let me start with alkene. Okay. Alkenes. Alkenes. Alkenes, the general molecular formula, that is CnH2n plus 2. For the general chemical formula is R or RH. R or RH. Where R is nothing but alkyl. R is alkyl group. Ready. If I have an alkyl methyl along with hydrogen, become an RH and you obtain methyl, an alkyl. Okay. The very same R methyl, when it is coupled with another methyl, this is in the pattern of RH and this is in the pattern of RR. Both are alkene. Ready. So RR or RH is the general formula, chemical formula of an alkene. Ready. And alkenes are also known as paraffin. Also known as paraffins. Ready. They are also known as paraffins. Paraffin means less reactive. The term means less reactive. Okay. Paraffin or less reactive. Enough about the introduction. Moving to there are actually 5 sections from an organic compound: nomenclature, isomerism, preparation, physical property, chemical property. You know the nomenclature of alkane, alkene, alkyne, benzene. Okay, in this chapter we have to discuss alkane, alkene, alkyne, benzene, 4 hydrocarbons. Okay, and the nomenclature is already over of your alkane. Ready? And you know the isomerism of alkane. Alkane can show chain isomerism, position isomerism, moreover conformational isomerism. Conformational isomerism. You are familiar with the eclipse staggered forms of ethane, propane, butane, like that. Okay? So simply isomerism, listen, can show chain isomerism. Alkene can show chain isomerism if the carbon number is 4. Alkene can show chain isomerism if there are minimum of 4 carbons. What are they? Normal butane. What is this one? What is this one? CH3, CH2, CH3. Normal butane, which is an isomer with the isobutane. CH3, CH3. 2-methyl propane. Isobutane. They all belongs to normal butane, which means butane. IUPAC name butane. This one have 2-methyl. IUPAC name of 2-methyl propane. So what is the difference? The difference is in the main chain, right? Difference is in main chain, which means they are chain isomer. Okay? And it can show position isomerism. Alkene can show position isomerism if there are 6 carbon. 6 carbon. Okay. Let the molecule be this 2, 2. This is 4, 2, 2. Dimethyl butane. Ready? Where its position isomer is 2, 3 dimethyl. So what is the difference? The main chain and branch are all are same. Branches, main chain, all are same. Two pairs is said to be chain isomer if their main chain if having a difference or a branch having a difference. Okay, listen. These two belongs to chain isomer. This is dimethyl cyclohexane. The main chain is cyclohexane, but the branches are dimethyl, and this is ethyl cyclohexane. Both having same formula, but the change is in branch name. Okay, so that belongs to chain isomer. Ready? Chain isomerism arises either main chain changes or branch changes. Ready? Here, main chain, branch all are remain same, but the position of a branch changes, so belongs to position isomer. Ready? And the next isomerism that is shown by your eye is stereo isomerism, where it is said to be conformational isomerism. Conformational isomerism. You know, you then have two conformers, mainly two conformers. What are they? What is this one? Eclipse, right? This one is eclipsed. Is it okay? Eclipsed. H. And this sigma bond can pre-rotate. I think you are familiar with that. If the sigma bond is pre-rotated, like this, and this is said to be staggered. Ready? But the diagonal angle is 0 here, 60 here. So alkene can show conformational isomerism. Conformational isomerism. Cycloalkene. Isomerism, right? Cycloalkene. This can show what? Geometrical isomerism. I think you are familiar with that. Geometrical isomerism arises when there is a rotation restricted center. Rotation restricted center. You know, double bonds are rotation restricted center. Ready? Like that. Any two corner or any two carbon in a cycloalkane ring is a restricted rotation center. Okay? So across that restriction rotated center, if the stereos are changed, then it can show what? Geometrical isomerism. I think you are familiar with that. This is a stereo arrangement of what? Dimethyl cyclohexane, CH3. What is the difference? This is a rotation restricted center. Okay, so it can show, or if there any change in the stereo array across this restricted center, then it is said to be geometrical isomerism. Okay, listen. Here also there is a change in stereo arrangement, right? Of this group, right? A change in stereo arrangement of this methyl group. Now it is in coincide with or in a parallel fashion with this one, but here it is inverted, right? But this change in stereo arrangement is by means of bond rotation, by means of the rotation of sigma bond. Okay, so that belongs to conformational isomerism. Here also there is a change in configuration. Listen, these two methyls are in wedge. This is wedge. I think you're familiar with that. This is wedge. These two methyls are in a same plane. Let it be the ready. And the stereo, or this, if these two are in a backward plane, which means these two are in the same plane, right? Either front or back. It is said to be the cis form. Okay. And if it is like this is said to be transform. Listen, this is cis form and this is the transform. Okay. And the change in stereo is not through bond rotation. This sigma bond is not able to rotate, but there is a possible change in stereo arrangement. So these tools are said to be geometrical isomer. Geometrical, if the stereoisomerism or the change in stereo which arises due to the non-rotation of bond, then that arrangement is said to be geometrical. If it is by means of rotation, then it is said to be conformational. So alkene can show, cycloalkene also belongs to alkene. Alkene can show geometrical isomerism. Wait, it can also show what? Alkene can also show optical isomerism if minimum of at least 6 carbon. Listen, here is a carbon. You know that a molecule to be optically active if it have a asymmetric carbon, chiral carbon. Okay, a molecule with one chiral carbon is always optically active. Ready? So alkene can, let me make this carbon as a chiral one. So simply a methyl group, a hydrogen, a ethyl group, a propyl group. So the all 4 groups are different. So this carbon is a chiral carbon, which means it can show optical isomerism. How much carbon? For an alkene to show optical isomerism, minimum requires 1, 2, 3, 4, 5, 6, 7. Right? 7, right? 3, 7. Minimum 7 carbon. So alkene can show almost all isomerism. Okay. If you want, you can copy that. And this is discussed in your basic organic. Okay, the very same molecule can also show optical isomerism because these are chiral carbons, okay? These all are chiral carbons. Let's check the valencies of this carbon. One is methyl, one is hydrogen. To the left, CH2. To the left, CH2. To the right, CH3. To the right, CH3. So all four valencies are different. Exactly very same. This is also identical, okay? So that can show geometrical isomers also. Sorry, optical isomers also. So now we are with the preparation. For that, I think you are familiar with the nomenclatures. It is required here. Preparation. Preparation of alkene. Preparation of alkene. Okay. The first method, that is from, so that is said to be hydrogenation of unsaturated hydrocarbons. What is said? Hydrogenation of unsaturated hydrocarbon. Hydrogenation of unsaturated hydrocarbons. Hydrogenation of unsaturated hydrocarbons. Okay, hydrogenation of unsaturated hydrocarbons. Ready? Oh, the reagents are hydrogen in palladium over charcoal, hydrogen in nickel, hydrogen in platinum, etc. Ready? Listen. I have a molecule CH3, C triple bond, CH. This is an unsaturated compound said to be propine. Ready? And the next is CH3, CH double bond, CH2. Propene unsaturated. Okay. And in an isomerism sense or in a double bond equivalent sense, one ring that is simply equivalent to one double bond. One ring is equivalent to one double bond. Okay, one ring is equivalent to one double bond because if I have butane, CH3, CH2, CH2, CH3. In an equivalency sense, one ring is equivalent to one double bond. If I have butane, CH3, CH2, CH2, CH3, what is the formula? C4H10. Okay, if I am removing two hydrogen from here, I can make this compound as CH3, CH double bond, CH, CH3, which means alkene. Okay, and the formula will be C4H8. By removing two hydrogen, I can make this as CH2, 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 cyclobutane. So what is the formula? C4H8. Okay. So from a particular compound, if I introduced an unsaturation, a double bond, or if I make it as a ring, both will be equivalent. Both are same. Okay. So one double bond is equivalent to what? One ring. So I have cyclopropane here. Cyclopropane. That means CH2, CH2, like that. Okay. Ready? And moreover, cyclopropene. If these all compounds which are hydrogenated in presence of anything like this, what happens? It becomes saturated. This cleft HH, one more HH. Here this bond is cleft to become propane. This is what? Propane. Here also propane. According to Bayer's strain theory or Sachet-Mort theory, cycloalkenes of 3, 4 carbons are unstable. due to angular strain. I think you are familiar with that. Okay. The most stable cycloalkene is cyclohexane. Cyclohexane. Then is cyclopentane. Then cyclobutane, like that. Okay. So cyclopropane is highly unstable. So on hydrogenation, this bond is cleaved. Okay. This is something like an unsaturation. H. So CH3, CH2, CH2. For this one, this bond is cleaved to become cyclopropane. Okay, and you know that cyclopropane further undergoes hydrogenation. So these twos are cleaved. Okay, to become the very same product. So all are what? All are propane. So this is the first method of preparation of alkene. Ready? Listen. If this is a molecule, what will be the product? What is this one? Butane. In bond line, it will be like this. Okay, fine. This is a molecule. It becomes cyclohexane, not hexane. Okay. If this is the molecule, no reaction. This is a molecule, it becomes cyclohexane. Why? Cycloalkanes of carbon 5 and 6 are relatively stable. They will not undergo cleavage. Okay, like this. Cyclobutane may cleave. Okay, fine. But the unsaturated inside a cycloalkane may be affected. Okay, here what happens? Hydrogenation to the unsaturation, not to the ring. Ready? So from this example, I can conclude a point. Cycloalkanes of carbon 5 or above relatively stable. Okay, ready? Sure. You know the names of this molecule: propene, cyclopropane, and you obtain the product propane. Okay. hydrogenation. Okay, that's the question. How many possible alkanes in hydrogenation of that typical molecule? Okay. So the chances are the ring is cyclopropyl. Okay, so the ring may cleave. So the first chance here. Okay, the whole bonds may be cleaved. That's a possibility number one. Or the second chance here. Ready. Or the third chance here. So what about the product in the first chance? Listen. This is cleaved. So here become CH3, CH2, CH2. Okay, so you obtain normal pentane. Ready? Is it okay? Number two. Okay, here is the cleavage. Ready? What it is? Isopentane. Or 2-methyl butane. What about the 3? Number 3 is what? This one. This is very same. Normal. So how many products? Okay, because there are 3 chances, right? But 1 and 3 are same. Okay.
The first one, double bond should be cleaved, no sir.
Double bond?
Double bond should be cleaved, no sir. The ring should be there.
No. Both may be cleaved.
In the single one, both will be cleaved.
If they said that hydrogen is 1 nickel, then the ring may cleave. Here it is, you have excess hydrogen. Okay, so cleavage of double bond followed by the ring may take place. Since it is a ring of 3 carbon, have high angular stream. Ready? Like this. So you should give the answer 2 possibility. Okay, 2 possible alkane. There are 3 possibility, or 1 and 3 are same. So there are 2 different alkanes can form, norepentane and isopentane. Okay, and hydrogenation using hydrogen in nickel is an example for cis addition. That means if they may ask on the basis of stereo, then you have to know that it's a cis addition. Listen, we have cyclohexene. Ready? And this bond is cleaved where 2 hydrogens are added. Okay? And the hydrogens may be in a cis pattern. The added hydrogen should be in a cis pattern. That is the concept. Okay, these 2 hydrogens may arrange in a cis pattern. They may be in the same plane. Okay. Either both are wedge or both are dash. They should be in a front plane, towards the front plane, or in a back plane. hydrogenation of alkene or alkyne using the catalyst, hydrogen, palladium, nickel, platinum, like that, to form alkene, and that is said to be Sabatier-Senderan's reaction. Sabatier-Senderan's reaction. Okay, and it follows free radical mechanism. Listen, free radical mechanism. Radical mechanism. No need of studying the mechanism, just know the mechanism. Hydrogen nickel means nickel is a good adsorbent, where hydrogens are chemisorbed on the surface of nickel. Okay. So on exciting they become hydrogen free radicals. Hydrogen radicals. And they cleaved the bond here to become radicals and added in the pattern. Okay. So you simply know that this follows radical mechanism. Okay. Hydrogen free radicals are added actually. That's all about the first one, hydrogenation of unsaturated hydrocarbons. The second one from alkyl halide, second method from alkyl halide. From alkyl halide. There are actually 4 methods from alkyl halide. Okay. So one by one, A, B, C, like that. Okay. From alkyl halide, you know what is alkyl halide? In bracket RX, alkyl halide in bracket RX. The formula is RX. From alkyl halide in bracket RX. Okay. Number 1, from alkyl halide in bracket RX, the first method, reduction using nascent hydrogen. Reduction using nascent hydrogen. Nascent hydrogen, you know, newly formed hydrogen. Okay, newly formed hydrogen. Nascent hydrogen. Listen. So the agents which can produce nascent hydrogens are, if we have zinc in hydrochloric acid, that forms nascent hydrogen. Or zinc in sulfuric acid is enough. Or zinc in acetic acid is also okay. Ready? Or the couple of zinc with the copper in methanol. Okay? They all can produce what? Nascent hydrogen. Listen. Then what is the reaction? The reaction is very easy. If I have RX, haloalkane, alkyl halide, which on treatment with the zinc in H plus, where the nascent hydrogen is produced. So this halogen replaced by hydrogen. Okay. And what do you obtain? RX become. What is RX? Alkane. So haloalkane become alkene. Ready? If I have an example, CH3, CHCl, CH3, which on reaction with the zinc in H plus, it forms CH3, CH2, CH3, where chlorine is replaced by hydrogen. Okay? Usually RX not equal to RF. Normally the alkyl halide is not belongs to fluoroalkane. Okay? Why means it is much difficult to cleave in fluoroalkane. The bond that have to cleave is carbon, where this require high this reaction is not feasible. Okay, so the alkyl halide may be chloroalkane, bromoalkane or iodoalkane, not fluoroalkane. Fine. The reaction is easy. Ready. Your halogen simply replaced by what? Hydrogen. And you obtain RH become RH. Can you question that? Class. Okay. B. Second method. Method B. By SN reaction of SN, nucleophilic substitution, SN. By SN reaction of hydride ion. Second is the SN reaction of hydride ion, bracket H minus. Hydride, H minus. By the SN reaction of hydride ion. Okay. So we have alkyl halide, ready, which undergoes nucleophilic substitution with the hydride donor. Okay. And the hydride donor which readily substitutes the halogen. The very same reduction you obtain RH as the product. Okay. So the halogen replaced by H minus. And this is a nucleophilic substitution. Then the hydride ion donors may be lithium aluminum hydride in this way, LaH, or sodium borohydride, maybe in this pattern NBH, okay, or pH thrice. Yes, thrice means triphenyl. Your pH is benzene ring, phenyl. Triphenyl tin hydride. Okay, and this is abbreviated as TPH. So these three may be the hydride donors. Okay, but conditions are there. This alkyl group may be a primary, or it may be a secondary, or it may be a tertiary. If the alkyl group is tertiary, then LiLH4 may bring it into a elimination. So for this substitution, tertiary is not okay with the LiLH4. If the tertiary alkyl halide with LiLH4, it may be leads to elimination. Okay. So for this reaction, LiLH4 is not suitable with the tertiary. Like that, NaBH4 is not suitable with the primary. This is the condition. Okay, listen, if I have a molecule CH3, CH Cl, CS3. Okay, which one reaction with the LAH, which one reaction with the NBH, which one reaction with the TPH. Is there any problem? What about the degree of this molecule? The halogen is attached to this carbon, which is branched to 1, 2. So this is there is no restriction for secondary, right? Okay. So in these three, the reaction is okay, where the halogen is replaced by hydrogen and obtain propane. Okay. Listen, if this is a molecule which on reaction with the LAH, there is no substitution. It may be elimination because this molecule is a chlorine attached carbon which is branched to 1, 2, 3. Tertiary. If it is NBH, it become isobutane, right? This is replaced by hydrogen. Okay, but in bond line, this much will be there. Ready? This is replaced by what? Hydrogen. Okay. So obtain isobutane. So the second one, the very same reduction, but it is not using nascent hydrogen from a hydride donor. Molecule is third butyl chloride and the formed alkane is isobutane. Why it is not third butane? Can write the possible products. This is what? Primary, right? So no problem with the LiLH4, but here there is no reduction. Why this third butyl chloride become isobutane? There are actually butanes. What are they? Normal butane and isobutane. Listen. But if we replace the hydrogen, we have two possibilities. This is identical with this one, right? These two are same. These two are same. So we have two possibility to remove hydrogen from here. That is either from the terminal end or from the second one, right? So this become normal butyl. Normal. If hydrogen is replaced from here, it become normal butyl. If it is replaced from the second one, it become sec butyl or sec butyl, secondary butyl. Like that, we have isobutane. Here also two different positions. What are they? This CH3 is identical with this one also. You know the shape. This is isobutane, right? Okay. So these three are identical with this point. Okay. There are two different hydrogens. One is and this is a tertiary one. Okay. So we have two possibilities to remove hydrogen from that. The one is from the end. One is from the end, and you obtain isobutyl. Or one is from this junction, okay, and you obtain butyl. So there are actually 4 alkyl groups, okay, but on supplying hydrogen it become 2 alkene. So this is third butyl. If here is a chlorine, it become third butyl chlorine. But the chlorine is replaced by hydrogen, it become what? Isobutane. That's why it become isobutane. Ready? So actually 4 possibility for alkane, but on supplying the hydrogen, it compressed to 2 alkane. Ready? Like that, we have one propane, that is normal propane, and you have two different hydrogen. What are they? These two are same. So one is this one, another one is this one. If I replace the valency from the end, the group is said to be N-propyl. Replace the valency from the center, group is known as isopropyl. But on supplying the hydrogens, it compresses. So 2 propyl, 1 propane. Okay. Like that. There are 8 pentyls. 8 pentyls and 3 pentane. 3 pentane, isopentane, neopentane, normal pentane. Only 3 pentanes are there, but 8 pentyls are possible. 8 pentyls. Like this, pentanes are possible. Okay. This you have to know in this you have to know because in your alkene, this is very much important. Okay. So this third butyl chloride become isobutane, not third butane. There is no third butane. The third butane is simply said to be isobutane. If you supply hydrogen to the tertiary carbon, it become what? Isobutane. So there is no third butane. Okay. type, that is Woods reaction. First of all, you have to know the reagent, that is sodium in dry ether. Okay, and the role of dry ether, that is to keep sodium as dry. Okay, if there is no dry ether, sodium Na become NaOH in presence of moisture. Okay, if Na become NaOH, the Woods reaction will not take place, and that will be explained on the basis of mechanism. Listen. So in Woods reaction, if you have two equivalent alkyl halides along with the sodium, and it should be dry ether. Okay, so these two halogens may go with the sodium, and the two alkyl group coupled to form a alkene of what? Rr. Okay, you simply remove the halogens and couple the alkyl group and you obtain RR type alkene. Okay, listen, the mechanism is actually free radical mechanism. Okay, that is, we have alkyl halide with the sodium. Ready? In presence of sodium, this bond may cleave by homolysis. Only in presence of what? Sodium. Okay. Normally, the carbon halogen bonds are cleaved like this. Become C plus and X minus. Halogen require extra electron. But here, the extra electron will be supplied by sodium. Okay, so sodium offers that it will supply one electron. Then the halogen cleaved in a homolytic pattern, and it become what? R dot and X dot. Okay, for that X dot, the sodium supplies electron. Okay, so that it become X minus. If one extra electron is gained by your halogen, it become what? X minus. Ready? If the sodium supplied one electron, it become Na plus. They will be combined. What is the next one? Alkyl radical, right? There are more than one alkyl radical in that system, right? So that alkyl radicals are combined to form RR alkene. Okay, so this reaction proceeds in a free radical mechanism if and only if sodium supplies electron to halogen. Then only the cleavage homolysis. Otherwise, the cleavage will be heterolysis. Okay, so here the cleavage is homolytic because the sodium offers one electron to halogen. For that, your sodium should be sodium. For that, it should be in a medium of dry ether. If there is no dry ether, sodium may be hydrated to become NaOH. Then there is no donation of electron from sodium to halogen. Then Woods reaction will not take place. Okay, so your sodium should be exist as sodium. Then only the mechanism takes place. Okay, fine. The mechanism is not given in your textbook. If you want, you can show that. Okay. And here we have three possibilities actually. Simple Woods reaction, crossed Woods reaction, internal Woods reaction, like that. Okay, usually if a reaction is between two molecules, listen, if a reaction is between two molecules, then we have three possibilities. Usually, simple, crossed, internal. Okay, let me discuss that. First of all, copy this one. are simple woods. Simple woods. In bracket, simple woods reaction means the two alkyl halides should be the same. They should be same. In bracket, between two same RX. Between two simple woods reaction. In bracket, between two same RX. If the Woods reaction is between two same RX, then it is said to be simple Woods reaction. Listen. Let I have two alkyl halide which on reaction with the sodium in dry ether, and you know that it become RR. And this is said to be simple Woods reaction. What is the speciality of the reaction? You always obtain a symmetric alkane. Symmetric alkane, because with respect to this bond, these two are same, right? Okay, these two are same because the reactions between the same alkyl halide. So with respect to this bond, here and here are same. So the molecule is said to be symmetric alkane. Symmetric alkane. So your even number of carbon. Okay. If I have a molecule with odd number of carbon, so no need of mentioning 2 here always, okay? We simply assume that it requires 2 equivalent. Okay, so simply CH3Cl with the sodium either is enough. Okay, we have here is 2 equivalent. Okay, fine. So this is a alkyl halide methyl chloride of carbon product. What is R here? CH3, right? R is? So what is RR? CH3? CH3. How much carbon? 2 carbon. Moreover, a symmetric. We are the very same. CH3. Which one is? This is R. So RR means CH3, CH2, CH2, CH3. How much carbon? 4 carbon. Moreover, a symmetric alkane. Okay. I'll give you more examples. So the first one is simple Woods reaction, and the speciality is you obtain symmetric alkane with even number of carbon. That's the condition. Okay, all have sodium in dry ether. Ready? And these all are simple Woods reaction, and we have to consider 2 equivalent. What about the R? R is isopropyl. There are 2 chances for propyl. If it is in a straight pattern, N-propyl. Otherwise it is isopropyl. Okay, so this is isopropyl. So two isopropyls are coupled, right? So this is first isopropyl, which is coupled with the very same isopropyl to form 2,3-dimethyl butane. Well, this is a symmetric one with a even number of carbon. What about this one? Listen. What about this one? Which one is the alkyl group? This is the alkyl group, right? Right. CH2, CH, CH3, CH3. Isobutane is the alkyl group. Okay. So the alkane will be Are you okay with that? This is a symmetric group. Is it okay? Okay. This much is R. Okay. So two same kind of R's are coupled. This is R. Here also R. What are same? Okay. Then what about the next? Show that. You should be familiar in bond line also. Okay. So there is a chance for forming a compound like this, right? If this methyl is on the top, no problem. Okay. What I say? Okay, fine. But this will not form. Okay. If the alkyl halide is a tertiary, then there may be a chance for elimination in presence of sodium. Okay, so substitution will not increase. There may be a chance for elimination in presence of sodium. Here the alkyl group is tertiary. I think you are familiar with the beta elimination. In elimination, whatever be the mechanism, E1, E2 or anything, if the reactivity order will be tertiary greater than secondary primary. So if there is a tertiary alkyl halide with you, then there is a chance for elimination always in presence of a base like sodium. Okay. So elimination means nothing but it is beta elimination. You know this molecule CH3, CH3. You are familiar with the beta elimination. This is elimination alpha. Beta, function group from alpha and from beta. And this molecule is third butyl bromide. What about the product? CH3, CH3, double bond, CH2. And this molecule is said to be isobutene. Why? Because this is isobutane, that's why this is isobutene. Sorry, not this one. This is This is isobutane, agreed. There are two butane, N-butane and N. So this molecule is isobutane. So this is isobutene. Got the idea? Fine. In most questions, names are given. Elimination of third butyl bromide become isobutene like that. Okay. So they will not mention it as in an IUPAC pattern like 2-methylpropene. It will be in a most simple pattern, isobutene. So you have to know what is isobutene. Then only you can choose the choice. Okay. So you know isobutane, it becomes isobutene. If this is a ethane, if replacing two hydrogen it become like that. You know, the compound is isobutane. If replacing two hydrogen, isobutene. But it is from third butyl. Third butyl on substitution forms isobutane. On elimination form isobutene. Keep it in mind, okay? There is no terbutene, terbutane. Both are isobutane. Okay. So if alkyl halide is a tertiary, so simply you cross this one, okay? If alkyl halide is a tertiary, then a chance for elimination to become alkyl. That you have to write in there, okay? You cross this one, okay? Then you write if alkyl halide is tertiary, then chance for elimination to form alkene, okay? Ready? What about compound? Right? How it is named? 1, 2, 3. This is the parent. Parent name is cyclopropyl. For the one half cyclopropyl group. One cyclopropyl. One cyclopropane. Okay, that's how you name. And you know, this one is 1 chlorocyclopropane. 1 chlorocyclopropane becomes cyclopropyl. Cyclopropane. The reverse concept may ask. That is, if you have what? Alkyl halide, which on reaction with the sodium in dry ether, and they may say that you obtain an alkane of Ra. Okay, then you are asked to find alkyl halide. What do you have to do? You simply cleave. The reverse may ask. Okay, you may be given with the product, and you are asked to find the reactant. Okay, so you know what is Wood's reaction. So you simply cleave the symmetric area and place two halogens on both carbon, and you simply write one among that. Okay, this one or this one? I'll give you one question. So show this much. So reverse may ask. Maybe like that. So A on reaction with the sodium in triether, it forms 2,5-dimethylhexane. Then what is it? So first of all, you have to design the structure of 2,5-dimethylhexane and think like this. Okay, cleave the symmetric portion and place halogen. Ready? And they said that A having a molecular formula C4H9 Cl. So the halogen is chlorine. Okay. So that's a reverse idea. Okay, you got the product. 2,5-dimethyl hexane, or in a bond line or in a condensed, whatever it may be, that's up to you. So CH2, CH2, CH, CH3, CH3. This is a molecule. Ready? So find out the symmetric portion and cleave the, since it is a C4H9Cl, you can place chlorine there. Okay, and your molecule is CH3, CH3, CH2, Cl, exhibited chloride. Okay, so question may ask like that also. Ready? So enough, that's all about simple Woods reaction. Moving to the second possibility in Woods reaction, that is crossed Woods reaction. Crossed Woods. Woods is enough. Crossed Woods. Crossed Woods means we know that we require two alkyl halide, right? Or we require two carbon halogen bond. That's a correct idea. We require two carbon halogen bonds. Two carbon halogen bond. We simply remove the halogens and coupling the carbons. That's the idea. If the two carbon halogen bonds are from same molecule, then it is said to be simple Woods reaction. If it is from different molecule, it is said to be crossed Woods reaction. Okay, so which means from different alkyl halide. And if two same carbon halogen bond from a single molecule, if two carbon halogen bond is from a same molecule, then it is said to be internal Woods reaction. Will be discussed later. Okay, now it is crossed. Crossed means different between two different RX. Okay, so in bracket between two different RX. Crossed Woods in bracket between two different RX. Okay, so listen. If I have one alkyl halide as R1X, R1, and another as R2X, where R1 and R2s are different, which are sodium in triether. Okay, and you know the mechanism of this reaction. Sodium may supply the necessary electron for halogen, and there may take place the homolysis, right? So what are the possible free radicals formed here? R1 free radical, you know the mechanism. So there are chances for the formation of R1 free radical or R2 free radical. Okay, and there may be more than one R1 free radical and more than one R2 free radical. Okay, fine. If they said that one equivalent R1X, one equivalent R2X, then only you can assume that here one R1X, one R2X. Else there may be a chance for more than one R1X and more than one R2X. Keep it in mind. Okay. So what are the chances? There may be a combination of R1 and R2 free radicals to form R1 R2 alkane. R1 R2 alkane. This is the perfect crossed one. Cross. Ready? And we know that there may be a chance for more than one R1 in that system, right? So the next possibility is between R1 and R1. So there is a chance for simple also, not only the cross. Ready? Like that, there may be the existence chance for 2 R2. So it will be R2, R2 also. So actually, 3 possibility always if there is a cross Woods reaction. Okay, listen. This is symmetric alkane, right? This also is symmetric alkane. Agreed. This may be, and this should be unsymmetric alkane. Unsymmetric with respect to this bond. Unsymmetric alkane with respect to that bond. That's always right. This should be unsymmetric with respect to that bond. But the molecule may be symmetric. Why? Listen, I'll give you an example. If I have one CH3, Cl, another one CH3, CH2, Cl. These are two. These two are entirely different weight. Let it be like that. Okay. Tell me the products. This is R1 and this is R2. The products are, the cross one is CH3, CH2, CH2, CH3. This is a crossed alkane, right? And this is symmetric alkane. But the bond formed is here. Agreed. So with respect to this bond, it will be unsymmetric. But the molecule is symmetric. So keep it in mind, right? Okay. So plus the next is CH3, CH3. And the next is CH3, CH2, 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 CH3. Ready? Okay, show that. Give one example. So actually these all are symmetric alkene, right? Okay. With even number of carbon, agreed. But there is a chance for unsymmetric alkene with odd number of carbon in your cross-Stutz reaction. Okay, listen. If I have the molecule CH3Br with CH3 CH2Br, what are the possibilities? Either CH3 CH2 CH3. This is an unsymmetric. Agreed? How much carbon? So odd carbon. Okay, there is a chance for unsymmetric alkane in Stutz reaction with the odd number of carbon, and it should be crossed one. Okay. Chance. In crossed one, there may be a chance for symmetric also. Okay. What about the next one? CH3, CH3. The next one? CH3, CH2, CH2, CH3. Listen. Not a best method. Not a best method for what? For unsymmetric alkane. Cross-Stutz reaction is not a. Stutz reaction is actually the best method for preparing symmetric alkane. Not a best method for preparing unsymmetric alkane. Because along with this unsymmetric alkane, there are two another also. This is propane. This is ethane. This is, they are neighboring members, right? So they have small difference in their boiling point and melting point. So their separation is very much difficult. It is very difficult. It is very difficult to separate your propane from ethane and butane. So this is not a best method for preparing unsymmetric alkane like propane. Okay. So Stutz reaction is not a for preparing unsymmetric alkene. There is a chance for formation of unsymmetric alkene, but it is not a best method because separation from the mixture difficult, right? Separation from the mixture is difficult. Okay. So in the previous case, we already written that in simple Wurtz reaction, we obtain symmetric alkane with the even number of carbon. But in Wurtz reaction, there is a chance for unsymmetric with the odd number, but it should be crossed. It should be crossed. Okay. And moreover, it is the best method. Not a best method for enzyme alkane because the separation from the mixture is difficult. Okay. Can you prepare methane from Wurtz reaction? No. For preparing methane, the possible chance is a crossed one like this one. Ready? But this is not a Wurtz reaction. Wurtz reaction at least require one carbon. A coupling reaction is minimum required one carbon. That's the condition. If these two are reacted in presence of sodium, there may be a chance for formation of this one. Okay, but it is not Wurtz reaction. Okay. This is not what? Wurtz reaction. Okay, this is another reaction, not Wurtz reaction. So, for the preparation of methane by Wurtz reaction, there is no possibility. Okay? Ready? This is not Wurtz reaction because Wurtz reaction minimum require one carbon. Okay, here there is no carbon. In this reactant there is no carbon, so it is not a Wurtz reaction. Okay, so this is the possibility for making methane, right? But it is not considered as what? Wurtz reaction. So it is clear that there is no chance for making methane from Wurtz reaction. Okay, and this is not considered as a Wurtz reaction. Because for the coupling of Wurtz reaction, it requires minimum one carbon. And the question may be asked like this also. And this is also a question from your crossed Wurtz reaction. What is the question? What about the maximum number of carbon by a Wurtz reaction between C2H5Cl and C4H9Cl? 8, not 6. Okay, this is actually a crossed Wurtz reaction. Agreed? Agreed. This one have 2 carbon. 4 carbon. Okay, you have to consider 3 possibility here. That is the idea. Okay, if you consider 3 possibility here, then there is a chance for the coupling of these two, and it leads to 8 carbon. So that will be the maximum. Agreed. So if you are simply given with the 2 alkyl halide for crossed Wurtz reaction, you have to consider 3 possibilities. Okay. Then only you can choose the choice as B. You should consider 3 possibilities. Even they are given like this. Okay. So for cross reaction there is 2 possibilities. Okay. So that all are the questions from cross reaction. Right, one more. Okay. So A plus B in sodium triether forms isobutane. Then what is A and B? Okay, you know the structure of isobutane, but you have to know. Then you can design easily A and B. Check it. This is okay. Maximum of what? Not 6, 8. Okay? Because there is a chance for the simple Wurtz reaction between the alkyl halide with the 4 carbon. Okay? The products are your hydrogen. Isobutane, CH3, CH3. Even though this is unsymmetric alkane, the chance is only 1, right? If you cleaved here, you obtain methyl and isopropyl. Or if you cleaved here, you obtain methyl and isopropyl. If you cleaved here, methyl and isopropyl. So there is only a combination possible. X. You don't know about the halogen. So CH3X plus CH3, CHF, CH3X. Okay? Fine. And that's all about Cross-Wurtz reaction. Moving to the next, internal Wurtz. Internal Wurtz. Internal Wurtz. Okay. Internal Wurtz means we already said that we require 2 carbon halogen bond. We simply remove the halogen and connect the carbons by an extra bond. Okay. If the 2 carbon halogen bonds which exist in a single molecule, then it is said to be simple Wurtz reaction. Okay. So the molecule, the Wurtz reaction is within a molecule actually. Within a molecule. So in bracket, within a molecule. Not between 2. It is within a molecule. Okay. So you may obtain compounds other than alkane, like alkene, cycloalkane. Okay, not alkene, but this is a case of Wurtz reaction. Ready? Listen, CH2Cl, CH2Cl. This is a Wisnel dichloride. If this is some simple Wurtz reaction with the sodium in triether, what happens? This chlorine moved to form ethylene free radical, agreed? This may be the free radical formed, right? They combine to form alkene, not alkene. Not alkane, you obtain alkene. And this is a Wurtz reaction because the reagent is very same. What? Sodium in, but this taking place in a same molecule. Okay, so if you have alpha beta compounds, you obtain alkene. If you have alpha beta halogens on Wurtz reaction, what do you obtain? Alkene. Okay, if you have, listen, if you have terminal halogens, they become cycloalkene. Huh? What about the free radical formed? This cleaved. The free radical is CH2. This is a CH2 free radical. They combine to form cyclopropane. Okay, if they are in a relative terminal position, there may be a chance for ring. Okay, is it okay? Like this. How much carbon in a terminal position? How much carbons? 1, 2, 3, 4, 5. So there will be a chance for ring of 5 carbon. Agreed. Listen, if they are in a diagonal position, what about the free radical formed? Okay, so they combine to form a bridge molecule, you know, bridger compounds. If they are in a diagonal position, so the chances are entirely different in your internal Lorentz reaction. If they are in a neighboring position, alpha beta position, maybe a chance for alkene. Terminal position, cycloalkanes. Diagonal position, bridger compounds. Okay, simply the logic is this one. If you know that it is a Wurtz reaction by looking to the reagent and you are given with 2 halogens, simply remove the halogen and make a bond. Okay, it may be alkene, cycloalkene or anything like that. And if it is in the same molecule, then it is said to be internal Wurtz. So these all are what? Internal Wurtz. Check the maximum possible. Check the maximum possible products of following. Check the maximum possible products of following reactions. Okay. you are familiar with the conjugation resonance of free radical. Conjugation of free radical. Listen. Resonance of free radical in your organic basic principles. You are given the free radical. If it is in a conjugated form, it may be rearranged. What about the resonance? This radical carbon asks electron for. This radical carbon may ask electron for this one. So this bond homolytically cleave to distribute the electron as like this, and this may be form a bond. Both the free radical will be in the middle of the carbon, right? Okay, ready? Like that, this carbon may ask electron for this one. So this is cleaved like this, and these two combine to form a bond here. The free radical will be here. This is the conjugation of what? Conjugation of free radical in a conjugated system. Okay, and you can show this one in this way also. CH2 double bond, CH double bond, CH, CH2. You can show this one like this. If this, okay, this radical will be here. That's the second structure, right? Agreed. Or if here is the and this bond will be jumps to here, and the radical will be okay. Actually, the radical is exchanged through like this. Simply, this is the rearrangement. Okay, so you simply show this much at least, or simply understand that you can apply here. Oh, this is a case. So you should do this in a mechanism pattern. You know what happens? There is only one chlorine, right? So there is a chance for simple reaction. Okay, there are two different one crossed. If there is only one chlorine, chance for simple. There is only simple. We have more than one halogen, so chance for internal. So here only simple. Agreed. Then what about the mechanism? Listen, CH2 double bond, CH, CH2 a bond. Agreed. This is a radical formed. Okay. So there may be a chance for rearrangement of that radical. Okay. So if it is rearranged, what about the CH2, CH double bond, CH2? But unfortunately both are identical. It's only one possibility. Agreed. Let this be the radical number A. This be the radical number B. What about the chance? So there are actually three chances, right? More than one A's are there. More than one B is also there. Ready? What about AA? CH2 double bond. CH2 double bond. CH2. That is what? AA. What about BB? Finishing. Same. B and A are same. So BB, AB, AA all are same. Actually three possibility, but unfortunately all the three are same. If here is a CH3, then it will be different. If here is a CH3, then all the threes are different. Okay, I'll give you a question like that. Okay, so you have to consider the rearrangement of free radical if there is a rearrangement. Free radical may be conjugated if a multiple bond is nearer to it. Okay, keep in mind. Fine. So here only that is either AA or AB or BB. Both are all are same. This is a radical A, radical B. Whatever be the combination, AA or AB or BB, you obtain the very same product. Okay. I'll give you another question like this, Lisa. What about the chance here? So there is an identification mark, possibly a chiral carbon, whatever it may be. This is a chiral carbon. How it become a chiral carbon? What are the valencies? Bromine, hydrogen, towards the left, CH2, to the right, C double bond. All are different. Okay. If there is no bond, then it is a chiral. Okay, if there is no bond, then it is achiral. Achiral means no chiral carbon. If there is a bond, then it is asymmetric. Okay. What are the chances? If bromine is cleaved, there is a chance for this radical. Agreed? Okay. Well, this is the star. Okay. What about the rearrangement? Let this be A. What about the rearrangement? This bond jumps to here. Radical will be here. Agreed. Still the star is here. Is it okay? Still the star is here, bond is here, radical is here. And this is B. What about AA? AA. AA is what about the nature of A? Free radical is in star and bond is to the allylic of that star. Allylic means alternate. Okay. So star is here, here also the star, here is a bond, here is a bond. This AA. Okay. What about BB? BB. Where is the free radical? In case of your B, the free radical is 1, 2, 3. Third position corresponds to a double bond. Okay. So these two are connected. Okay. Where here we have a bond, here also we have a bond, and to the terminal of that bond we obtain star. Is it okay? What about AB? Here is a star. Okay. So there are actually 3 different products. Okay. Chance for 3 different if your radical is rearranged. Keep it in mind. Okay. Wait, what about here? I'll explain the whole. Here is a chance for, listen, here is a chance for 3 different types of radicals. Possibly 2 different types of radical. One is this one. Okay. 2, sorry, not 2, 3. The second one is this one. The third one both may cleave. Okay. Since this is in a diagonal position, they readily forms a brittle compound. Like this. If there are 2 molecules like this, then there is a chance for there may be a chance for 2 of this radical. So the chance is something like in your relative opposite position, chlorine. And what about here? Bromine. Or there may be a chance for they are cross, right? Okay, and we can say that this may be the major. Here Why? For this one, the cleavage of which bond taking place? For making this molecule, two CBr bonds are cleaved. Two CBr bonds are cleaved. For making this one CBr, one CCl cleaved. For making this one, CBr bonds are cleaved. If there are two, then two CBr bonds are cleaved. For making two CCl. Which bond cleavage is require less energy? Carbon-bromine bond. Carbon-bromine bond easily cleaved, easily break. Okay, so it is very easy to, or it is very feasible to break two CBr bonds. So this may be the major. Okay. Now, what about here? That's a chance for. There may be chance for two types of radical, either this one or this one. Agreed. So the chances either a bridger or either bridged or something like this. Okay. Is it okay? Since here both are different, the chance will be increased. Here both are same, only two chance. Ready? This will be the maximum case in your Roots reaction, maximum. For your NEET examination, this is not required, just try and done. Okay. This is a maximum. Ready? So you may think like this also.